Hello students and welcome to the 19th lecture on particle physics. Yesterday we were discussing about the charmonium and botonium states, and we discussed that this is a CC bar and BB bar quark anti-quark states, and the particles in the different states have been experimentally observed, and this is the table which is showing the different existence of different CC bar and BB bar mesons having different angular momentum, parity, and C parity. That means these three are representing the properties associated with the different observed mesons. We saw that the parity is obtained by parity of the fermion like C, parity of the anti-fermion C bar, minus 1 to the power L, the relative orbital parity between C and C bar states. And since by hand we assign even parity to the fermion and odd parity to the anti-fermion, therefore this product is minus 1, and then we have minus 1 to the power L. Therefore overall we have minus 1 to the power L plus 1. And for C parity we saw that C parity is given by minus 1 to the power L plus S. Therefore if we talk about a particular principal quantum number n equal to 1, that will have L equal to 0, and there are two fermions, they are spin half particles, and therefore the total spin of the states can be spin singlet or spin triplet state. Now an atomic state is represented by twice S plus 1 Lj. Therefore we had 1 as S is 0, L is equal to 0, that corresponds to a S state, and J, L is 0 and S is 0, J is 1. Then when L is 0 and S is 1, J is 1, therefore this is 1, and L equal to 0 again corresponds to S state, and 2S plus 1 will give us 3. So therefore this is another state. So therefore what we have? We have a state 1s1 and 3s1. 1s1 is an independent state with principal quantum number 1 and orbital quantum number 0, and then the C parity associated with this is minus 1 to the power L plus S, and that is L is 0, S is 0. This will be minus 1 to the power 0. This is plus 1 or even. And parity, that is minus 1 to the power L plus 1, as we have discussed earlier. Therefore, this will be L is 0, this is minus 1 to the power 1, that means minus 1. Therefore, this state we represent it with JPC. J is, as you can see, L is 0, S is 0, J is 0, parity is minus, and C parity is plus. Therefore, this corresponds to a state with angular momentum 0, parity negative, and C parity even. Now, if we talk about this guy, then in this state, C parity will be minus 1 to the power L plus S, and L is 0, S is 1, therefore this is negative, and parity minus 1 to the power L plus 1, L is 0, therefore this is negative. Therefore this state will be J is 1, L is 0 and S is 1, parity is negative, C parity is negative, therefore this is 1 minus 1. Therefore first state has 0 minus plus, the second state has 1 minus minus. Similarly, if we talk about n equal to 2, then it will give us L equal to 1 and L equal to 0. L equal to 1, in this state again spin can be 0 or spin can be 1. Now if L is 1, S is 0, my J is 1, then parity is minus 1 to the power L plus 1, and that is minus 1 to the power L plus 1 is 1 plus 1, that is even. And C parity minus 1 to the power L plus S, this is equal to L is 1, S is 0. Therefore, this is minus 1 to the power 1 plus 0, and that is negative. Therefore, this is 1, J is 1, parity is positive, and C parity is negative. Therefore, this state is represented by 1 plus minus for n equal to 2 and L equal to 1 and S is equal to 0 for principal quantum number n equal to 2. Then we have L equal to 1, S is equal to 1. This will give us J is equal to 0, 1, 2 from L minus S to L plus S. Therefore, for L equal to 1 and S is equal to 1, our J is 0, 1, 2. Then we will talk about that. That means we have 0, 1, 2, the J that we represent. And then for parity, you see this is minus 1 to the power L plus 1. Therefore, this is even for all the cases. And C parity minus 1 to the power L plus S, and L plus S is even. Therefore, this is even. Therefore, you have different states with 0, 1, 2, J having parity and C parity, both of them positive. Then one is n equal to 2, L equal to 1. The other possibility will be L equal to 0. And then corresponding to that, you have S is equal to 0 and S is equal to 1. You can again use the same formalism to get that. And that is why you see we have different J's, different P's and different C's. And we have 1s0, 3s1, 3p0, etc. states. And corresponding to these states, we have observed different CC bar and BB bar mesons in the experiments, and these are the excitations of the resonances, and they say that these mesons are not fundamental particles. They are made up of some fundamental particles. Okay. After this, here we have shown a general spectrum of the particles which we have shown here. This is 2984 MeVs. Therefore, in GeV we can write it at 2.984 with J is equal to 0, parity is negative and C parity is even. You see, J is 0, parity is odd and C parity is even, and we have 2.981 resonance. Similarly, other resonance for the CC bar mesons, and similarly we have that for the BB bar mesons. Now after that, what we discussed in the class was about the charge conjugation violation in weak interaction, and what I had told you that all neutrinos are left-handed and all the antineutrinos are right-handed. Left-handed means spin of the particle is in opposite to the direction of the momentum of the particle, and right-handed means the spin of the particle is in the direction of the momentum of the particle. This is, we are representing a neutrino, and in the second case we are representing an antineutrino, where you can see that momentum and spin both are aligned in the same direction. Now, if we have a left-handed neutrino and we operate by a charge conjugation operation, then what we realize is that charge conjugation vibration does not disturb spin, it does not disturb linear momentum. What it does, it makes a particle or brings the particle to an anti-particle state, and therefore this will become nu bar. And similarly, a nu bar right-handed will become nu with the charge conjugation operation. And nu bar means spin and momenta, they are not unchanged. Therefore, it remain left-handed, and we know that left-handed anti-neutrinos have not been observed. Similarly, right-handed neutrinos have not been observed, and therefore C is not a good quantum number in weak interaction processes, while we saw that is good quantum number in electromagnetic and strong interaction processes. Then we discussed about the Goldhaber experiment, and this I told you that this is the beautiful tabletop experiment which showed that helicity of the neutrinos are left-handed. Though never a neutrino was observed, but the experiment was designed in such a way that the information observed for the photons reflected the information about the neutrino. And what we had discussed in the class, that European nucleus with spin 0 and parity even was taken, and through an electron capture we had a samarium star with spin 1, and besides that a neutrino was emitted. Therefore, this reaction gave rise to samarium star and neutrino exactly in the opposite direction. And as you can see that this capture was taken place in the atomic S state, therefore L was 0. That is why the total angular momentum of the initial state was 0. From European, and spin is half, therefore 0 and half gave us J is equal to half. Now if J is half, while here what we are finding out that neutrinos are the spin half particle, while samarium star is spin 1 particle. Therefore, to conserve angular momentum, initial angular momentum is half, the final angular momentum should be half, then that means the spin of the angular momentum of the samarium star should be opposite to the angular momentum of the neutrino, and therefore either these angular momentum will be like this, exactly opposite in direction, or we can say that the angular momenta are opposite and in this direction. Therefore, angular momentum are, we have drawn in such a way that angular momenta are opposite in this case as well as in this case. But there is a catch here. This samarium star, when momentum and spin are in the same direction, this is representing a right-handed state. Similarly, this neutrino is representing a right-handed state. While here, when we are trying to have J equal to 0, in this case, then neutrinos are left-handed. Therefore, in one case it is right-handed and the other case it is left-handed. Now, you may ask the question, why neutrinos are coming in the right hand side direction, why not to the left hand side? You can equally think of the same. Neutrinos are coming to the left hand side direction and samarium star is coming on the right hand side direction. Now here also, if you consider the angular momenta, either angular momenta will be in the exactly two opposite direction like this, or the angular momenta like this, which we have shown, will be will give us J is equal to half. Therefore, again, we will have a right-handed neutrino or we will have a left-handed neutrino. Now, the important catch is samarium star has a definite lifetime, and as it is moving in the opposite direction, it emits a photon and comes to the ground state. That ground state is samarium with J is equal to 0. Therefore, the important catch is this samarium star is getting emitted. It has got a certain lifetime and it comes to the ground state by emitting a photon, and it transfers its angular momenta to the photon because this ground state has angular momentum 0. Therefore, the hard work was for the choice of the nucleus which captures the electron, goes on to excited state, and then the de-excitation gives a nucleus which has J is equal to 0, and it transfers its angular momenta to the photon. Therefore, notice that the photon's direction is opposite to because samarium is moving in this direction, it is releasing a photon. Photon is moving in this direction. Therefore, as you can notice, the direction of the momentum of neutrino is exactly opposite to the direction of the momentum of this photon. And that means, again, if you consider the angular momentum conservation, that means if this is a right-handed neutrino, then we are talking about the right-handed polarization of the photon, or if this is a left-handed neutrino, then we are talking about the left-handed polarization of the photon. The important point is that if we measure the polarization of the photon, from there we will say that the neutrinos are left-handed or neutrinos are right-handed. For example, if we say that in the experiment we are seeing equal number of left-handed and right-handed polarized photons, then that means in the experiment we are getting equal number of left-handed and right-handed neutrinos. But what was observed that we get right-handed photons, we never get a left-handed photon, which would imply that we have always left-handed neutrinos and never a right-handed neutrino. Therefore, the important point was never a neutrino was seen. We measured the polarization of the photon, and from there we inferred the polarization of the neutrino, that neutrinos are left-handed. Therefore, the choice of the parent nucleus which captures the electron, the excitation of the samarium nucleus with J is equal to 1, and then coming to the ground state by transferring its angular momenta to the photon was the important catch. And the helicity of the neutrino was decided by measuring the polarization of the photon. This is what we had discussed yesterday, and we had stopped at this point. Therefore, to directly measure the helicity of neutrino, physicists needed to find a radioactive source that would have three spatial properties. What are they? The initial nucleus would have an orbital angular momentum 0, and spin angular momentum is always 0, such that J is equal to 0. This was one choice. The other choice was this nucleus captures an electron, resulting into an excited nuclear state, plus it releases neutrino. Neutrino comes out, and to conserve the lepton number, the excited nucleus spin angular momentum should be 1. This excited nucleus must decay to ground state such that the ground state nuclear spin is again 0. We have samarium in the ground state, and the angular momentum is carried by the photon. There should be a magnetic field, direction of which may be altered. One time we will see that it will be in clockwise direction, and another time it will be in the anti-clockwise direction. The other important point was that the orbital electrons captured by the nucleus are almost entirely s electrons. That is why L equal to 0 we are talking about. Therefore, spin of the electron is half. Europium is a spin 0 nucleus, and therefore L is 0 and S is equal to half for the electron, while S is 0 for the europium nucleus. Overall, there is no orbital angular momentum. It is in L equal to 0 state, and then S is half, such that J initial is half. Therefore, the final J should also be half. And this is what we are discussing, that electron has J equal to half, europium has J is equal to 0, such that it is giving us samarium star with J is equal to 1, besides a neutrino with J equal to half. And this samarium star has got a finite life. It then, as it moves forward, it goes to ground state and it transfers its momenta to the photon and also its angular momentum to the photon. Therefore, now the photon is moving in the forward direction and with an angular momentum 1, and neutrino has, we had J equal to half. Therefore, this is the scenario which I was discussing previously. Therefore, you can say that the momentum and spin of the neutrino are in the same direction to have the total angular momentum half, or to have the angular momentum half. Here this neutrino is becoming left-handed while this neutrino is right-handed. If equal number of photons we are going to observe in the left-handed and the right-handed polarization states, then we will say that we have left-handed as well as right-handed neutrinos. Now what I will talk about, that this samarium star is releasing a photon and coming to the ground state, and the momentum as well as the spin of the samarium star will be carried by the photon, and therefore the photon is getting emitted in the opposite direction of the neutrino. As well as to conserve angular momenta, here the photon has the same helicity as that of neutrino. Or here if we talk about photon is getting emitted in this direction and angular momentum is being transferred, this is J equal to 1. To conserve, again the initial state has J is equal to half. Therefore, to get J equal to half, these angular momenta should be exactly in the opposite direction. Now notice that in both these scenarios, the nucleus recoils away from the neutrino. See, either we are talking about here, or we took another case where neutrino is coming on the right direction and samarium star is moving in the left direction. This gives the same scenario, and a measurement of nucleus helicity will also provide the neutrino's helicity. Now furthermore, the excited nucleus decays to its ground state by emitting a gamma ray. So the nucleus helicity may be measured from the observed polarization of the forward emitted photons. Therefore, this is the excited photon with J equal to 1. It is coming to the ground state with J equal to 0 by emitting a photon which is carrying the angular momentum of the samarium star. Therefore, we have the scenario where neutrinos and photons are getting emitted in opposite direction, and to conserve angular momentum, either the neutrino will be right-handed or the neutrino can be left-handed. And if neutrino is left-handed, photon is also right-handed, photon is also right-handed. If neutrino is left-handed, then photon is also left-handed. And there is no third choice. And that is why if we are measuring the polarization of the photon, from there we will infer the helicity of the neutrinos. If samarium star decays at rest, then the emitted gamma rays have been observed to have 960 kilo electron volts of kinetic energy. In the above example, since samarium star, as we can see, in this picture, it's in motion. It has got some kinetic energy. Therefore, the emitted gamma rays has energy which is slightly larger than this 960 keV. And that plays a very important role, that the samarium star, when it is in at rest, it emits a photon to come to the ground state by emitting a photon of energy 960 keV, while samarium star, which is in motion, which has got a certain kinetic energy, when it is emitting a photon, its kinetic energy, the kinetic energy of the photon is slightly larger than when photon was being emitted at samarium star at rest. Therefore, what you are noticing, that we have to measure the polarization of the photon to infer about the neutrinos, whether we say that neutrinos are coming on the right hand, in the right hand side direction, or it is coming in the left hand side direction. This will be opposite to the direction of the emission of photon. Now for this, what was done? European nucleus was kept in a magnetic field, and then a detector was placed here, sodium iodide detector, to detect gamma rays. And in between this source and the detector, a lead shield was placed to avoid the background. Then at these two ends, which has been shown here, samarium scatterer were placed. This was placed to have resonant scattering. That means, why we talked about samarium star is in motion, and therefore the photon that will be emitted will have kinetic energy slightly more than 960 keV. This was required to have this resonant scattering, because those photons will be absorbed by the samarium scatterer. The other photons of other kinetic energy won't, and therefore when it will absorb and place in this direction at say 45 degree, it will re-emit this photon in this direction, and this photon will pass through sodium iodide detector, and we will be sure that these photons are coming from the emission or the release of photon by the samarium star nucleus. When it was coming to the ground state, it released a photon. Therefore, the important point was that this source was kept in a magnetic field, and there was samarium scatterer. This was placed at an angle at which these photons being released by the samarium star, they can be absorbed and re-emitted. And this re-emission of the photons, these photons, they pass through this sodium iodide detector to give us the count. Therefore, the source is placed in a magnetic field. The gamma rays are emitted in all directions, but the gamma rays emitted towards the detector are those that will be analyzed. A cone of lead is inserted between the source and the detector to avoid gamma rays from the surroundings. Those will get absorbed. The gamma rays emitted opposite to the nu, as we have discussed, must have slightly higher energy than the 960 keV typical of gamma rays from the decay of samarium star at rest. This means that samarium star will be able to reabsorb and quickly re-emit gamma rays. In the samarium scatterer, it will reabsorb and re-emit the gamma rays that are emitted by an atom identical to itself in a process called resonant scattering. The advantage is that the resonant scattering acts as a filter that only reabsorbs and re-emits gamma rays of such energy and not the gamma rays of other energies in the vicinity. Therefore, it is playing the role of filter. That is very important. It is only seeing those photons which have kinetic energy slightly higher than 960 keV. The other photons won't have this resonant scattering phenomena. Now, as I have told you, the source was placed in a magnetic field. And we know that when we have a magnet, there will be electrons in the electromagnet. These electrons will have certain spin. Those are in the electromagnet. The electrons spins in the magnet align anti-parallel to the magnetic field. This spin may be in the direction of the emitted photon's spin or opposite to the direction of the photon spin. See here, what I am telling you, that the magnetic field and the spin direction of the electron in the magnet, they are oppositely directed. Now photon does not know about it. Therefore, photon which is being released will be either in the direction of the spin of the electron, or it can be opposite to the direction of the spin of the electron. This is what I am talking about, that the photon, those are being released by samarium star. Either that will be in the direction of the spin of the electron, or it will be opposite to the direction of the spin of the electron. Now, what's important, that if it is in opposite direction of the spin of the electron, then electron in the magnet can absorb this photon, and the spin of this will be flipped. Therefore, while the photon spin which is in the direction of the spin of the electron cannot absorb this photon, because for electron's spin is half, angular momentum is half. Therefore, this can only happen when the spin of the photon is in the opposite direction of the spin of the electron. Therefore, an electron in the electromagnet with the spin sigma opposite to that of a photon can absorb a unit of angular momentum by spin flip like this, which I have shown. If the spin is parallel, it cannot do that. Now, if this is so, that means if the gamma rays are polarized in the same direction as the magnetic field, then electrons of iron in magnet are more likely to absorb the gamma rays. Gamma rays of one polarity would be transmitted. That means where they are in the same direction, it cannot take the spin of the photon. Therefore, these gamma rays will pass through, while if it is in the opposite direction, the gamma rays, the energy will be used to flip the spin of the electron. Therefore, in one case, these photons will come out, but in another case, these photons cannot come out. Therefore, gamma rays of one polarity would be transmitted, and those of other polarity would not be, because energy will be used to flip the spin of the electron. Therefore, gamma ray transmission is greater for the left-handed polarized photons than for the right-handed ones. Now, when you change the direction of the magnetic field, then the spin direction will get changed. Now, what will be expected, that in this case, the photons which were not being seen, now they should be seen, because now they will have a direction. This guy is getting emitted. Now electron's spin is in this direction. Therefore, now it will absorb this photon and it will flip its spin, while here it will be in the same direction when you reverse the magnetic field, and therefore it won't absorb those photons. Therefore, in one case, you will get from this. In another case, when you do the magnetic or reverse the magnetic field, you will have the equal number of photons coming from the case where photons are being absorbed by the electrons to change the change the spin of the electron. Therefore, once it will be right-handed and another time it will be left-handed. But if nature handles both of them equally, then we should expect that there should be equal number of photons in when the magnetic field is in one direction, and then when the direction of the magnetic field is reversed. But what was the observation? The observation was when the magnetic field was set up to absorb right-handed photons, plenty of left-handed neutrinos were present to set off the detector. When the magnetic field was set up to absorb left-handed photons, the detector fell silent. Therefore, here in the previous case, left-handed photons were seen, and that means left-handed neutrinos were getting emitted. Now, when we turn the magnetic field in the opposite direction to control the left-handed photons, they will be used to by the electron to absorb to take energy and flip their spin. Now we were expecting that we must have the right-handed ones, but what was seen that the detector fell silent, and therefore it was concluded that nature did not allow right-handed gamma rays to come out because the right-handed photons would imply right-handed neutrinos. Therefore, never right-handed photons came out when the direction of the spin was moved from clockwise to anti-clockwise direction, and therefore from here it was seen that only we see left-handed polarized photons. Therefore, by measuring the polarization of the photon, it was inferred that all neutrinos are left-handed in nature. This experiment concluded the fact that neutrinos are left-handed, and then similarly the experiment was done to see that anti-neutrinos are right-handed. Thank you very much.